We build multi-agent AI systems to simulate human policy debates, but they consistently fail at the one thing they're supposed to do: disagree. When you assign different value perspectives to different language models, they still converge on the same option. We call this artificial consensus. And in normative deliberation, where no objectively correct answer exists, convergence isn't a success metric. It's a failure mode. Today, we're breaking down a new framework called the AI Council, which tackles this problem through architectural heterogeneity and a novel coherence validation layer. The research runs entirely on consumer hardware using 7 locally hosted 7 to 9 billion parameter models, and it reveals something counterintuitive about how model diversity actually works when there's no ground truth to converge on. Let's start with why artificial consensus happens in the first place. In multi-agent systems, 2 main forces drive convergence. First is shared inductive bias. When every agent runs on the same base model, they share the same training data, reinforcement learning preferences, and reasoning patterns. Even with different system prompts, you're essentially asking the same reasoner to wear different hats. Second is debate capture. During structured argumentation, agents assigned to minority value perspectives get swayed by the majority's arguments and abandon their assigned viewpoint. Recent work shows this isn't just blind sycophancy. It's structured, asymmetric persuasion that depends heavily on model architecture and prompt formatting. The AI Council addresses this with a 3-phase deliberation pipeline. Phase 1 is a structured debate where 3 champion agents advocate for different policy options. They don't just state positions, they critique alternatives through their assigned value lens. Phase 2 is independent evaluation. 7 evaluator agents, each primed with a distinct value perspective like security focus, risk tolerance, or pragmatism, read the full debate transcript and rank the options. Crucially, they don't see each other's output. Phase 3 is optional coherence validation, which acts as a post-processing quality filter. The system's core intervention is architectural heterogeneity. Instead of running all 7 evaluators on the same model, the researchers paired each value perspective with a different 7 to 9 billion parameter model. These models come from different organizations, use different training methodologies, and include instruction-tuned, code-specialized, and reasoning-optimized variants. The results are stark. In a child welfare policy scenario, first-choice concentration dropped from 71% in the homogeneous baseline to 46% with heterogeneity. In an urban housing scenario with genuinely competitive options, it dropped from 46% down to 23%. Both differences are statistically significant with large effect sizes. This finding directly contrasts with accuracy-oriented multi-agent debate. In factual or mathematical tasks, heterogeneity doesn't reduce convergence because the evidence itself points to a single correct answer. But in normative deliberation, where convergence is driven by shared training biases rather than objective truth, breaking that shared architecture is exactly what's needed to preserve legitimate disagreement. Now the second layer is coherence validation. After evaluation, a frontier model assesses whether each evaluator's reasoning is genuinely grounded in its assigned value perspective. The frontier model only sees the perspective definition and the reasoning text, not the votes or policy options. It returns a coherence score between 0 and 1. These scores are then used as weights in a modified Borda count. In an unweighted system, every vote counts equally. In the weighted system, each evaluator's points are multiplied by their coherence score. Low coherence evaluators still contribute, but proportionally less. This preserves all votes while downweighting voices that failed to reason from their assigned values. But here is where the research reveals a structural tension, the fidelity-diversity tradeoff. Coherence validation doesn't always preserve disagreement. In the child welfare scenario, it worked as intended. The dominant option won most runs, but several evaluators agreed with it for the wrong reasons. Downweighting those low coherence majority voices amplified the minority dissenters, reducing concentration further. But in the housing scenario, the effect reversed. The highest coherence evaluators happened to cluster on a single policy option, while the perspectives providing genuine diversity were modeled by weaker reasoners with lower coherence scores. When coherence weighting was applied, it amplified the clustered high-fidelity voices and increased concentration. This isn't a bug in the validation layer. It's a fundamental property of quality-weighted multi-agent systems. When model capability varies across value perspectives, fidelity assessment and diversity preservation become competing objectives. The researchers argue that the right response isn't to abandon coherence validation, but to report both weighted and unweighted results. The gap between them tells you exactly which perspectives are being modeled reliably, and which require stronger underlying models. The study also documents hard constraints for small language models in deliberation. The team tested 3 Delphi-style interventions where evaluators were exposed to counterarguments or asked to self-reflect. All 3 failed. Peer exposure caused capitulation cascades. Value tension filtering destabilized agents. Self-reflection produced 0 vote changes because post-hoc rationalization exceeds self-correction capability at this scale. The consistent finding is that 7 to 9 billion parameter models exhibit a binary response to counterarguments. They either maintain their position entirely or capitulate entirely. There is no graded middle state. This means any multi-agent architecture that exposes small models to opposing arguments risks forced convergence, making isolation during evaluation a necessary safeguard. To measure deliberation quality, the framework introduces several diagnostics. First choice concentration tracks top option agreement. Border margin captures ranking depth. But the most useful metric is the trustworthy tension rate. This measures the fraction of theoretical value conflicts, where both sides reason faithfully from their assigned perspectives, whether they agree or disagree. Across both scenarios, roughly half of all theoretical tensions are trustworthy. This establishes a clear baseline. Current small model deliberation can maintain faithful value reasoning about 50% of the time. The rest is suspect agreement or partial coherence. So what does this mean for building multi-agent policy simulators? Architectural heterogeneity is no longer optional. It's the primary mechanism for disrupting shared inductive bias and preserving legitimate disagreement. Prompt engineering alone cannot achieve this. Coherence validation is a powerful quality filter, but it must be applied with full transparency about the fidelity-diversity trade-off. And for small models, we now have empirical evidence that structured isolation during evaluation is required to prevent debate capture. The AI Council doesn't prescribe policy answers. It maps the landscape of value-based trade-offs, flagging where perspectives genuinely clash and where apparent consensus is just spurious agreement. As multi-agent systems become standard tools for policy analysis and stakeholder simulation, understanding these structural dynamics will be essential. The research is openly available, and the framework runs entirely on consumer hardware, making it highly accessible for replication and extension. If you're working on multi-agent deliberation, normative reasoning, or AI-assisted policy design, this paper should be on your reading list. It doesn't just solve a problem. It redefines what success looks like when there's no right answer to converge on.